This is 2008 FRQ number 2, still in the calculator portion. It says concert tickets went on sale at noon where t equals 0. So this is noon. So of course this is 1 o'clock, 3 o'clock, 4 o'clock, 7 o'clock, 8 o'clock, and 9 o'clock. I assume that's when the show starts. So 9 o'clock is when, oh, it says when it was sold out within 9 hours. So I guess the show may not have started. The number of people waiting in line to purchase ticket at time equals t is modeled by a twice differentiable function L for between 0 to 9 hours. Values of L of t at various times are shown in the table above. So what is different this time is this is the actual function. So typically we're given the rate and you're supposed to use that to kind of evaluate the original function versus the slope or the rate of the rate of the rate. But this time we're actually given the original function. So this is our, in a way, f of x. And so from here, we can sort of see f prime, but f double prime is gonna be a little harder to see because we have to estimate that, where we don't have the exact function itself. We only have a table of values. It's gonna be a little bit harder to get the exact numbers, okay? So use the data in the table to estimate the rate. So rate is kind of like a derivative, right? Or a slope, if we remember that, at which the number of people waiting in line was changing at 5:30. T equals 5.5. I don't have t equals 5.5, but I know t equals 5.5 is between 4 to 7 o'clock. So what I can do is use our usual y2 minus y1 over x2 minus x1 to figure out the rate around that time, because that's in between those two numbers, right? Those are the two data points I have. So in part A, we're looking for L prime of 5.5. We're looking at the rate at 5.5 hours, and we're going to use y, the y value of 7 minus the y value of 4 minus over 7 minus 4, right? This is y2 minus y1 over x2 minus x1. Using my table of values, I get 150 minus 126 over 7 minus 4. That will give me 24 over 3, which is 8. So what does this mean? At 5:30 p.m. approximately, because about, we don't know for sure, right? Approximately, the line is increasing at approximately about 8 people per hour. That's the rate at which this is happening, okay? And that's it. Part B, use a trapezoidal sum with 3 subintervals to estimate the average number of people waiting in line during the first 4 hours that the tickets were on sale. All right, so first 4 hours, perfect, it's right here. Right? So the way you need to look at this is, again, these intervals are not equal. So you cannot use your usual formula to figure out the trapezoidal sum. You have to look at the interval between the t values or the x values and then use that as your height. And then the y values are your base 1 and base 2. So average in this case, because we're looking at the sum of an integral, the average is the formula of 1 over b minus a integral a to b of f of x dx, right? Well, 1 over b minus a, 1 over 4 minus 0, because it's the first 4 hours. This is the piece we need to use the trapezoidal sum because we do not have the actual function to find the integral. So we're going to use the trapezoid to figure out the sum. All right, so we're looking at the table of values up here. Let's see. The first trapezoid has a height of 1. So trapezoid, the formula for a trapezoid, to remind yourself, trapezoid is 1/2 base 1 plus base 2 times height, right? Or height over 2 times base 1 plus base 2. This is what we learned in geometry. So we're going to use that idea here. So 1/2, the height between these two is 1 times, these are the base 1 and base 2. So 120 plus 156. Next trapezoid, now it's these two values. 1/2, the height between 1 and 3 is 2. And then base 1, base 2. So now this is 156 plus 176. And then last piece of trapezoid is now these two. So 1/2, the height between these two is 1. And now you add these two bases, 176 plus 126. Okay, so do your calculation. I don't want to waste your time. But when you calculate all this out, the average in the first 4 hours is about 155.25 people. So you could really round it to 155 people because it's not really 0.25 people. Okay, all right. Let's move on to part C. between 0 to 9 hours, what is the fewest number of times at which the derivative t must equal to 0? Give a reason for your answer. So we're looking at when the first derivative equals 0, we're looking for an extrema. We're looking for whether you get a maximum or a minimum. So in this case, it's actually a little easier to kind of graph this out to get an idea of what the LT may look like. And then you can use that to justify your answer. So very quickly, we're going to go ahead and do a very quick function here. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10. Okay, and then for the y value, I need up to 176. So 180. All right, so let's see. We got 1, 2, 3, 4, 5, 50. 1, 2, 3, 4, 5, 100. 1, 2, 3, 4, 5, 150. 1, 2, 3, 4, 5, 200. Now, you don't have to be super exact, but at least you know the idea of where you're going. 0, 120. 1, 156. So 1, 156 around here. 3, 176. So 176, the highest point. 60, 70, 76. Great. And then 4, 126. Oh, sorry. 3 is right here. I went too close. Okay. All right. At 4, we are at 126. So 4, 126, a little bit more than my 0. Good. And at 7, so 7's right here. We're at exactly 150. 7's at 150. And then at 8, we are at 80 now. So 80, 8 is 80, right around here. And 9, we're back at 0. Okay, so what can I conclude? Well, I can see that at this point, this value up before and this value after is lower than this value here. So that could be a maximum, right? There could be more in between, but this is the least that we're going to suspect. And now if we look again, we're looking at the graph, it went up again. So because these two values are higher than that value, that could be a minimum. So here's a max, here's a min. And again, coming back down again, these two values are lower than this value. This is another max, right? So what can we say? Well, I can say that in 0 to 4, right, there is at least a max. Why? Because you want to talk about the fact that the value here is greater than the one before and the one after. So L of 3 is greater than L of 1. The value at 3 is greater than 1. And it's also greater than the one after it, right? So it's the highest number there. Therefore, it is a maximum. Okay, now in the next interval we're looking at is between here and here. So in 3 to 7, because these are only numbers I have, I can't use anything else, there must be a minimum. Why? Because the value at that point, 4, the value of 4 is smaller than the one before, and it's smaller than the one after, right? 4 is smaller than these two. All right, so you can probably guess the last one. In the last interval, between 4 to 9, because I need to compare these two, or I can compare the last one. So in 4 to 9, or you can say 4 to... well, yeah, 4 to 9. A max exists because, right, in 4 to 9, do you see how 7 is the highest number, right? So because L of 7 is greater than L of 4, and L of 7 is greater than L of 8, and you can say L of 9. So, yeah, either way works. All right, so now we've proven that at least 3 times the derivative must equal to 0 because I have 3 extremas. Okay? All right, last one. The rate at which tickets were sold between 0 to 9 hours is modeled by this R of t function for tickets per hour. Based on the model, how many tickets were sold by 3 p.m. to the nearest whole number? So because this is a rate and we're looking at how many total is being sold, you now need to use an integral. So the total number is going to be integral from 0 to 3 because it's 3 hours. The rate at which it is being sold, 550 t e to negative t over 2, all right, dt. Okay, so again, this is a calculator portion. You don't need to do this by hand. Let's use Math 9 again. So Math 9, function's 550, t, so use x, and then e to the negative x over 2. Close my parentheses, double check. 550t, 550x, e to the negative x over 2, comma x, comma 0, comma 3. Oops, comma 3. All right, so there you go. 972.78. We can't really have 0.78 tickets, so round it up to the whole number. So about 973 tickets sold by 3 p.m. Okay, that's it for number 2.